Namaste. Myself Rahul Sahu from Government Engineering College Raipur. Here we are at Heat and Mass Transfer Lab, and today we are going to perform experiment on insulating powder apparatus. So here the aim of the experiment is to determine the thermal conductivity of any of a insulating powder which is placed here. So let us briefly look at the description of the equipment, then we will move on to the calculation part, and finally we will get the thermal conductivity of the powder. So what is thermal conductivity? So basically thermal conductivity is the rate of heat transfer through a unit area by a unit temperature gradient. So the here the first one, as you can see, this is the switch on off key for the whole equipment. Second one is the voltmeter to note down the voltage supply to this equipment. The third one is the ammeter, which is showing 0.2 ampere at the present case. Third one is the digital display of the thermocouples placed inside this copper sphere. So at present it is showing 81 degrees Celsius. So we will discuss where is the temperature this 81 degrees Celsius, we will discuss after that. And this one is the dimmer state to increase or decrease the power supply. Here in the present case, as you are seeing in the equipment, here it is showing 233 volt and 0.2 ampere for the present case. If we decrease, so here it is approximately 233 volt. If we use voltage stabilizer, it can be reduced further. Ideally, voltage stabilizer should be used for this equipment. At the present case, our voltage stabilizer is not functioning properly, so the voltage is quite high for this equipment. We will see, we have already taken our steady state readings. We will see how the values come in case of the steady state. These are the dimmer, or these are the switches to change between different thermocouples. So here it is showing inner and here it is showing outer. We will see first what is inner and outer. Here, as you are able to see, this is a copper sphere. This sphere consists of two concentric copper sphere, one of having inner diameter, one of having in a diameter of 100 mm, and outer one, this sphere which is you are seeing in the equipment is outer copper sphere, which is having diameter of 200 mm. So there are two concentric copper sphere. The outer one is having diameter of 200 mm and inner one is having diameter of 100 mm. 6 thermocouples are placed inside the inner surface. That means 6 thermocouples are placed in the inner sphere and 6 thermocouples are placed in the outer sphere, and the space between the inner and outer surface is filled with the insulating powder. Here in the present case it is chalk powder. So, the space between inner and outer sphere is filled with an insulating powder, for which the thermoconductivity we have to calculate, and the heater, nichrome heater, is placed inside the inner sphere. That means, there is an heater at the center, then inner sphere, then outer sphere. Inner sphere having 6 thermocouples at its surface, and similarly 6 thermocouples at the outer sphere. So, when the steady state achieved in this sphere, power supply to the heater completely dissipates into the atmosphere, because in the steady state temperature or any other property of the material will be constant. That means, once the steady state temperature achieved, the temperature of the chalk powder will no longer be increased. That means, the complete power supply to the heater must be dissipated to the outer surrounding, so that temperature of chalk powder will not be increased. Okay. So, as I already mentioned, there are 6 thermocouples in the inside sphere and there are 6 thermocouples in the outside sphere. So, this switch which you seen in the middle of this inner outer, this switch what basically do is, basically if we move this key towards this this inner sphere, the all values will be of all values will be of inner sphere thermocouples. That means, okay. So, at present it is not a steady state case, we will see, we have already taken our steady state data. So, at present this switch is towards this inner sphere, and inner sphere is pointing towards 1, that means T1 is 46, similarly 45, similarly T3 is 43, and so on. So, if this key is moved towards this inner sphere, all the temperature readings from 1 to 6 will be displayed here, and once this key move towards this outer key, all the temperature readings will be of outer sphere. So, these are the temperature readings. I request my apology, because actually this name which is written here are opposite. This is inner sphere readings and this is outer sphere readings. So, the temperature at the inner surface is 93, at present it is showing at T5, then T6, similarly T4, T3. So, this is mystically this is written as outer or inner, but in actually it is inner and outer. So, inner, if this key move towards this one, all the temperature reading will be shown of inner sphere, and if this key move towards this, then all the temperature readings will be displayed of the outer sphere. So, this is how we will note down our readings. This is voltage, ampere, this is this, if this key move towards this one, all the temperature readings will be of outer sphere. If this key move towards this one, all the temperature readings will be shown, all the temperature readings in this digital thermocouple will be of inner sphere, and this is to increase or decrease the voltage supply. So, let's look on to the calculation part, how we calculate this thermoconductivity. So, here it is the concentric sphere of made up of copper. So, inner sphere consists of 6 thermocouples in the inside sphere, T1, T2, T3, 4, 5, 6, 6 thermocouples in the inside copper sphere, and similarly from T7 to T12 6 thermocouple at the outer copper sphere, and the space between this concentric sphere is filled with the insulating powder. Here it is a chalk powder. Okay. And at the center of this sphere there is a heater which generates the heat at the center, and if the steady state has already been achieved, the heat supplied to the heater must be dissipated to the surrounding, so that the temperature of this insulating powder will not be increased. That means, at the steady state the heat supplied to the heater must be dissipated to the outer surrounding, and the temperature, all the temperature values should be constant. This will be treated as steady state. So, we have to find out the thermoconductivity of the insulating powder which is placed inside this concentric sphere. So, T1 to T6 the temperature readings placed at the inside sphere, T7 to T12 thermocouples at the outer surface of the sphere. So, by the geometrical property we already know the inside and inner radius and outer radius, which is 100 mm and 50 mm, and for the steady state one of our steady state, we already noted down all the temperature readings which are as so average temperature inside the inside sphere are as follows. These are in degree Celsius. So, these are the temperature reading, these are the temperature readings at the inside sphere, and similarly from T7 to T12 outside sphere, outer sphere radius. So, these 6 are the readings at the inner sphere, and these 6 are the readings at outer sphere. And as you can see, there are temperature gradients between inside and there is temperature gradient at inside and outside sphere. As you know, this is what? This is Fourier law of heat conduction, which basically states that heat transfer through any surface is directly proportional to the area of heat transfer and temperature gradient across the surface. So, heat transfer is directly proportional to the area of heat transfer and temperature gradient along the surface, and this is proportionality constant, which is thermal conductivity, and negative sign represents that heat must be flow or heat will always be flow from higher temperature to lower temperature. So, this is the Fourier law of heat conduction equation. If we simplify this heat conduction equation for the present case, which is spherical, so for concentric spheres, radial heat transfer can be calculate as 4 pi thermal conductivity into inner radius into outer radius, temperature difference between both inner outer and thickness. So, this is the radial heat transfer flow between inner and outer. So, if we rearrange this equation, we will get thermal conductivity of the material between two concentric sphere can be find out by this equation, Q into thickness divided by 4 pi multiplication of both radii and temperature difference. So, in present case this all thermocouple readings are at inside sphere and this all 6 readings are at outside sphere. So, if we take mean of these 6 thermocouple in the inside surface, we will get the average inside temperature, average temperature at the inside surface. And if we take average of these 6 readings which is at outer surface, we will get average surface temperature at the outside sphere. So, average inner surface is the average of this 6 temperature, which come out to be 196.83 degrees Celsius, and average outer surface come out to be 62.833 degrees Celsius. So, this is the inner surface temperature, outer surface. We know this difference between we already calculated this temperature difference. So, we know this temperature difference, we already know these geometrical properties. Q is basically what? Q is this heat supplied to this nichrome heater, which is basically multiplication of V into I. For this temperature readings, our heat supplied was voltage approximately voltage was approximately 180 volt and ampere current was 0.1. So, it comes out to be 18 watt. So, at this power supply, this was the steady state temperature readings, and if we put all these values in this equation, we get 0.107 watt meter Kelvin as the thermal conductivity of the insulating powder. So, this is how we calculate our thermal conductivity. So, let us just summarize. There is 2 concentric sphere, inner and outer, and 6 thermocouples separately placed into the inside, separately placed into the outside. So, average of this thermocouples at the outside gives the mean average outer surface temperature, and average of inside thermocouple gives the average inside surface temperature. Once we know these temperatures and and heat supplied, we can easily get the thermoconductivity. So, it is 107 Kelvin. That means, this is the thermoconductivity of the material which is placed inside the concentric sphere. Thank you.